Hello and welcome to the fourth video on proof and logic. The goal for today's video is to be able to involve a little bit more math into what we are trying to do. So a lot of what we did in the previous videos was using like literal English sentences, and we convert them into symbols, and we use logic on those symbols. Now that's helpful, and we saw a bunch of applications to that, but the main topic of this whole video series is to be able to also involve math as well. So right now I don't think we'll be dealing with sentences anymore. We're going to convert mathematical statements into nice symbols that we can perform logic with. And the goal for today's video is to be able to use what we learn from this system over here and use it to construct our first proof. And as you can see, it will be an inequality proof. It's a really simple proof, very straightforward, but we will prove it with like hardcore logic, so it'll be totally overkill. Anyways, what inequality are we going to prove? We're going to prove that for all numbers a, b, and c, if a is less than or equal to b and b is less than or equal to c, then a is less than or equal to c. Pretty obvious, I'm sure you've seen this before a lot of times, and this is easy. It has a lot of proofs, most of them geometric. So if you have a on one side and b on the other, then this thing is true because a is indeed less than b on this number line, and we have that b is less than c, so c should be somewhere around here. And well, it's pretty obvious that a is less than c, so pretty straightforward, easy proof. But let's try to do it in a different way, with what we have learned with truth tables and equivalent statements and all that other stuff. But before we do that, let's have some experience with converting mathematical statements into symbols. And it's actually not that hard to do. It's pretty much exactly the same as when we're trying to convert a sentence into symbols. So you have a statement like Peter goes to Starbucks, which is the example from the previous video, and you give that the symbol P. So it's exactly the same thing with a mathematical statement. So if we have a statement such as 5 is less than 6, then you can give it a symbol. Let's say LT for less than. So there we have it. There's our mathematical statement, and we gave it a symbol. But it turns out we can actually do better than this. There is a problem with the way we are doing it currently, and it is because this is terribly inefficient. Because in most cases, you want to include a lot of statements in your truth tables. So you don't only want one statement. Maybe you also want to include 7 is less than 10, you want 10 is bigger than 5, and you want a bunch of other statements that you can fit into a truth table to observe any interesting relationships. But for each new statement, you have to give them a new symbol. But that is, like I said, terribly inefficient, because if you have lots of statements, then you have lots of symbols, and it gets really confusing to work with. Well, it turns out there's a brilliant idea to overcome this, and it's not actually that brilliant. I'm just saying that for dramatic effect. But what you do is you attach brackets next to a symbol, and then you write 5 on one side and 6 on the other side. So you have 5 and 6. So now our symbol reads 5 is less than 6. And it's easy to translate other statements into symbols as well, because if you have 7 is less than 10, we can just write that as LT 7 and 10 instead of giving it an entirely new symbol like Q or P or something like that. This is easier to read and it is easier to interpret because immediately based on the symbol, you can directly tell that this symbol is talking about 7 being less than 10. And maybe you can have another one, GT, for greater than, and anything else basically. And actually you can just do things in your own way as long as it's efficient. You don't want like 10 different symbols on your table. Basically, that's the point. So you can define your own language like what I have done over here as long as it's efficient. But the general strategy is to attach brackets and fit numbers onto it so that you can represent more numbers like this without having to define an entirely new symbol. Anyways, we have our language, we have our dictionary. We can now translate mathematical statements into symbols. So what are the mathematical statements that we're dealing with, right? We're dealing with A being less than B, and we are also dealing with B being less than C, and also C being, and A being less than C. So these are the three statements that we'll be dealing with, and it's easy to convert them into symbols. We can just say LTAB, LTBC, and LTAC. And like I said, it could work if you gave each one of these different symbols. You could let this one become like A, this one become B, and this one become C. You could give them those symbols, but it's more meaningful to give them these symbols instead for the reasons that I said earlier, and I hope it's clear and you can understand why we're using this instead of just making it A, B, and C. Although that might seem simpler, for more complicated examples, things will get like really disorganized, and you really don't want that to happen. Remember from last video, we talked about equivalent statements. So what do we want? We want to show that less than AB, and so the V here, wait, no, crap. This one here, this is and this is or, and you have to ingrain that in your head. You don't want to flip those two around. That's going to result in a hell of a lot of confusion. So just try to ingrain that in your head. So LTAB and LTBC is equivalent to LTAC. So if we can show that this statement is true, then we have completed our proof already. By doing this, we showed that this gives the same meaning or transmit the same information as this thing over here, meaning they are mathematically equivalent. Because like in English, we made an example earlier about two sentences conveying the same information. Now instead, we have mathematical statements which convey the same information. And we know how to do this already because we have the truth table at our disposal. So let's work on that. So we have our statements LTAB, LTBC, and LTAC. And we also have LTAB and LTBC. So let's just draw the columns over here. So this statement over here, it's basically A is less than B, right? So this statement over here, it can either be true or false because we don't know what A is, we don't know what B is. We just said that A and B could be any number. And obviously, it works for some numbers, like 5 is less than 6. That would be an example of the statement being true, but we also have other examples, like 10 is less than 5, and this is clearly not true. But since we said that A can be any number and B can also be any number, we should also consider this as a possibility. So this can be either true or false. And same goes with this guy as well, true or false. But we also have other possibilities. This can be true and this can be false, and this can be false while this can be true. Alright, what about the LTAC statement? So what about this things here, LTAC? So this is A is less than or equal to C. Well, this statement, we already know something about it. We know that if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. So we already know that this is true based on the number line that I drew earlier. And all we're trying to do now is we're trying to turn our argument from a geometric argument to a more logical argument. So we're going to use the information that we have from the geometric point of view. And the geometric point of view tells us that this over here on top, I'm just going to erase the arrow, should be true. Because, yeah, if A is less than B, true, and B is less than C, true, then A is less than C, true. And this is the only possibility. A is less than C can only happen when these two statements are true. That's the only possible way, that's the only possible configuration. And again, we can use the number line to prove these sorts of things. So everything else over here should be false. And to fill this table up, we basically used geometric information. And let's see if that matches up with our logical information. So let's use logic. So let's compare that with logic this time. So LTAB and LTBC. Now this is an AND statement over here. So this guy and this guy should both be true in order for our corresponding rows to be true. Now this is only possible in the first case over here, because this is the only universe, the only scenario where our LTAB is true and our LTBC is true. So we can say that this is true, and we can't say that it's true for any other possibility because it doesn't satisfy the AND condition. None of these statements are both true. Only one of them is true, at least. So all the other three possibilities fail the AND condition. And since they fail the AND condition, we give all these three possibilities an F. And would you look at that? Both of these are equivalent. So we can argue geometrically, and it gives us a bunch of statements. We can also argue logically, and it gives us a bunch of statements as well. And turns out they're equivalent. It's confirmed. The logic works, which, well, I mean, yeah, logic always works, so that's not surprising. So we've used this truth table, just this one piece of technology, and we have done so many things with it. We have proved a mathematical statement. We could also simplify English language, or basically any other language. And we have also used the truth table to figure out which arguments work and which arguments don't work. It's just this little tool, and it has so many different uses. It's so amazing. Yeah, there's a lot more to come. See you in the next video.